Good morning, students. To myself, Vijay Shankar, Electronics and Communication Engineering Department at Chevrolet Engineering College. Today, we are going to discuss about some more examples. These are fifth one. So briefly, I have to discuss about the spectral densities, energy, and the power spectral density, and you have to go for do some more examples. Some examples in the autocorrelation functions and the energy spectral density and power spectral density. So, the energy spectral density or energy density spectrum, both are the same. It is a distribution of power or energy. It is a distribution of power or energy of a signal per bandwidth as a function of frequency. Spectral density is nothing but it is a distribution of power or energy of a signal per unit bandwidth as a function of frequency. In that, the energy and the power signals, the signal which finite signals with finite energy and the power is equal to 0 is called energy signals. Example, a periodic signal like pulse. And signals with a finite average power and the energy is infinite. Remember these two. Energy is infinite. Then it's called power signals. Examples is a periodic signals. Energy of the signal x of t is defined E is equal to integral minus infinite squared magnitude of x of t. And the power signal is limit t tends to infinite 1 by t the integral t by to the t by 2 the squared magnitude of x of t dt. Okay. Once again, so energy spectral density is the distribution of power or the energy of a signal per unit bandwidth as a function of frequency. And we have the two signals. We have the energy and the power signals. Energy signal is signal with finite energy with 0 to infinite and power is a 0 is called as energy signals, and signal with finite energy average power 0 to infinite in between the 0 to infinite and energy is infinite here, then we can call it as a power signal. The energy signal definition is equal to integral minus infinite squared magnitude of x of t dt. The first one, the Parseval's theorem of energy signals or Rayleigh's energy theorem. We know the x of t, the Fourier transformation is x of f, and x star of t is a x star of minus f. The energy signal becomes the squared magnitude is x of t and x star of t. X star of t and x of t. Replace the x of t in terms of the inverse Fourier transformation. Inverse Fourier transformation is in the frequency f, there is no 1 by t. If it is a omega, we have the 1 by 2 pi is there. Now I am taking directly the x of f e power j omega t into df. There is no any multiplication of 1 by 2 pi. And you can use the omega, x of omega, e power j omega t. And d omega, there is a 1 by 2 pi minus 1. So inverse Fourier transformation, changing the order of integration, x of f, integral minus infinite x star e power j omega t dt. It is also the definition of the Fourier transformation, but there is a plus here. You can keep this a minus omega minus e power minus j omega t bt, then only it is a star. So I'm taking the whole star here, whole star, the function x of t e power plus is becomes of minus, so the x star of f into df. Okay, little bit confusion we are getting here. So I'm taking the integral minus infinite x star of t e power j, the omega, actually the omega is a 2 pi f minus 2. So no need whenever we are changing the f here, it is a 2 pi f. J 2 pi f into d t, here the dt is df, I am taking the outside dt. So integral minus infinite to infinite x of t e power, changing the plus as a minus now, and e power 2 pi f into t dt whole star. Now the above equation, the below equation, both are the same. So whole star x star of t, and plus in giving the minus, don't put it as a dt star and the dt like that. It is with respect to applying the minus infinite to infinite. So see, the definition is x of t e power minus j omega 2 pi f into t dt is a Fourier transformation. X of f, and here the whole star, x star of f. X of f and x star of s is the square magnitude of x of f. According to the Rayleigh's theorem or the Parseval's theorem for the energy signals. Next, energy spectral density. Energy spectral density. Separately, I am taking the energy spectral density. It is a distribution of energy of the signal in the frequency domain. In the frequency domain is called energy spectral density, or ESD or ED, energy density spectrum. Psi of f is equal to squared magnitude of x of f. What we got by using the Rayleigh's theorem, we got the squared magnitude of x of f is equal to the energy signal. E is equal to that is a psi of f, and that psi of f we can call it as energy spectral density. Let x of t and y of t be the input and output of the linear system, and y of t is a Fourier transformation is y of f, and h of f be the system transfer function. H of f is output by the input in the frequency, because spectral density is always in the signals in the frequency domain signals only. We can write the equation psi of f is equal to squared magnitude of x of f, and psi of f is a squared magnitude of y of f, because the suffix is the x and y is the y. So psi y of f is equal to the squared magnitude of y, and the y is nothing but h and x, h of f and x of f, the squared magnitude of x of and the psi x of f. So psi y of f is equal to squared magnitude of system function and psi xy of f, psi x of f. So energy spectral density of output is a product of energy spectral density of input, psi x of f, and square of the magnitude of the transfer function. Square of the magnitude of the transfer function. Transfer function means h. And coming to the power density spectrum, or power spectral density, it is a P is equal to limit t tends to infinite 1 by d the integral minus t by 2 the t by 2 squared magnitude of x of t dt. So only the difference is the limit t tends to infinite 1 by t, and the limitations only for the energy and the power signals in the continuous time signal. The Parseval's power theorem, the P is equal to sum of n is equal to minus infinite to infinite fn square. Okay. So the proof here, the Parseval's theorem for power signal. Here we are applying the Fourier series. So there it is a energy spectral density. To find the power signal, Parseval's theorem, we are using the Fourier transformation. This also we already discussed. Squared magnitude is x of t and x star of t conjugate functions. Substitute the squared magnitude as x of t and x star of t. And x of t, as per the exponential Fourier series synthesis equation, saying that x of t is equal to sum of n is equal to minus infinite to infinite. Fn is a x of k, my dear students. Remember here, don't confuse x of k. Here I wrote Fn. X of t is equal to sum of n is equal to minus infinite to infinite. Fn e power j n omega naught t. Actually, it is a k minus infinite to infinite fk e power j n k. Write as xn only. Replacing x of t in this equation by the equation 3. So p is equal to 1 by t integral minus t by 2 the t by 2 x of t I am substituting as this synthesis equation. sum of n is equal to minus infinity infinity fn e power gn omega naught t and x star of t dt. Interchanging the summation and the integration, 1 by t, the sum of n is equal to minus infinity infinite fn minus t by the t by 2 x star of t e power j n omega naught t dt. Again, change is as a whole star and it is a minus. The t by 2 to t by 2 e power minus j omega t dt is a exponential function. Exponential Fourier series is the analysis equation. What is analysis equation? 1 by t, the integral t e power x star of t e power j n omega naught t dt as a f n star fn star. So sum of n is equal to minus infinity fn star. That becomes of sum of n is equal to minus infinity the squared magnitude of x of n. So including the 1 by t, my dear students. Here the 1 by t is there, including this 1 by t and this total function. This 1 by t and this total function you can write as fn. And here I am taking the whole star. Okay, fn and fn star is the squared magnitude of fn. This is a Parseval's power theorem. Now coming to the power spectral density, the distribution of average power of signal in frequency domain. In frequency domain is called power spectral density. Power spectral density is always in the frequency domain function only. X of t is x of t, the t by 2, the t by 2. Let us assume the signal is at 0 outside the interval of t by 2, the t by 2, because we are not assuming the minus infinity to the minus t by 2, then t by 2, the t by 2. We assume that is a 0 for otherwise, and xt of t as in between of the signal only, the x of t, the tau function. So E is equal to energy signal. We can take energy is integral minus t infinite to the infinite x tau of t. It becomes of x of f using the Fourier transformation. There is a Fourier transformation relation of energy signal in the Parseval's theorem. X tau of t is the Fourier transformation of x tau of f. Okay. In the interval of minus infinite to the infinite, changes as minus t by 2 the t by 2 x of t square, and that x of t square in the power signal, the 1 by tau minus t by 2 the t by 2, and the similar way you can write as 1 by tau the minus infinite x tau of tf x tau of f square into df. Okay, so 1 by tau will get for the power signal. If tau tends to infinite, the left hand side, the equation 1 represents the average power P. Average power P. We call it as S of F. If t tends to infinite, integral minus t by the t by 2 x tau of F by the tau into df. This total function approaches to the finite value denoted as S of F. Psi of F is the energy spectral density. Now here the S of F is a power spectral density. So average power, the P is equal to x square of t whole bar is integral minus infinite S of F df. Or in terms of the omega, 1 by 2 pi into integral minus infinite x of omega into df, d omega. Got it, my students? As in the similar fashion of psi y of f is equal to squared magnitude of the system function is product of psi x of f. For the power spectral density for the periodic function also, we'll get the same function. Sy of f is equal to squared magnitude of h of f and s x of f. Okay. Now the comparison between of energy spectral and the power spectral density, it gives the distribution of energy of the signal in frequency. Power spectral densities, it gives the distribution of power of the signal in the frequency domain. and psi of f is the squared magnitude of x of f, and s of f is the squared magnitude of x of f with the tau is there 1 by tau, and the tau is tends to infinite. And total energy is given E is equal to integral minus infinite to infinite psi f of f, and the power is integral minus infinite to infinite s of f into df. So remember these two equations. The third point is very important. And the fourth point is a relation between autocorrelation, Fourier transformation relation for energy spectral density, and Fourier transformation relation for power spectral density also. So first you can see the relation between autocorrelation function and the spectral densities. The first property, the autocorrelation function R of tau of energy signal and its energy spectral density forms a Fourier transform pair Rxy of tau or xy of tau. Autocorrelation function is not Rxy, my dear students, or xx only. Okay, this is for cross correlation. If both the functions are the same, then the autocorrelation function is given R of tau is equal to minus infinite infinite x of f and x star of f e power j omega tau df. Okay, got it, my dear students? I'm taking here the r x y of tau in the right hand side. I'm writing in the frequency function, not in the time domain function. Observe here. Okay, x of f, x star of f e power j omega tau df. X star and the xf is the squared magnitude of x. And what is the squared magnitude of x of f is a psi of f. Okay, substitute there, it is a psi of f minus infinite infinite. It is the inverse Fourier transformation relation for the R of tau. So R of tau is a Fourier transformation relation of psi of f only. Got it, my students? And autocorrelation function is a Fourier transformation of the power spectral density. So S of f. So R of tau is equal to, I'm taking in terms of discrete time function, sum of n is equal to minus infinite infinite x of n, x star of n is a Fourier coefficients, x of n square e power j n omega naught tau. Okay, as a synthesis equation. That synthesis equation is left hand side is a time domain. Taking Fourier transformation on both sides. Fourier transformation, assuming this signal is a time domain signal. Take the time and domain signal and e power minus 0 omega tau beta. Interchange the orders and the integration value. Sum of n is equal to minus infinite infinite squared magnitude if you take e power minus j omega tau. Omega is a plus, minus, and plus is n omega naught beta. And becomes of 2 pi the sum of n is equal to minus infinite infinite the squared magnitude of x of n. And this integral value is a Fourier transformation of 1. What is a Fourier transformation 1? 2 pi into delta omega. 2 pi into delta, what is omega here? Omega minus n into omega naught. So Fourier transformation of 1. Here it is a 1 is there, my dear students. 1 with the exponential value. So 2 pi into delta of omega minus n omega naught. And that is equal to sum of n is equal to minus infinite infinite squared magnitude. If it is in terms of the frequency, you can change the delta function. 1 by 2 pi is there. 2 pi get cancelled. Psi delta of f minus n into f naught. Okay. Now you can observe here there is an inverse Fourier transformation relation. The Fourier transformation of R of tau is equal to S of f. Is equal to S of f. So R of tau is the inverse Fourier transformation of S of f. Therefore, R of tau is a Fourier transformation relation of the S of f. Got it? So that is the fourth point. And the relation between the convolution and the correlation, already seen in the last class, is a one signal is a normal signal and the other signal is a folded function. And for these two signals, convolution only is equal to the correlation. The first point, in the correlation, the physical time t places the role of dummy variable of it, and it appears after solving the integral. But in the convolution, delay parameter tau plays the role of a dummy variable. Correlation or xy of tau is a function of a delay parameter with the tau, whereas convolution is a function of the time. Correlation can be obtained by convoluting x of t and y star of t, because it is a folded function. Convolution does not depend on which the function to be shifted, whereas correlation closes the convolution is a commutator. So see, the convolution, the correlation are identical for even signals. For even signals, you see the R12 of tau, x1 t minus tau, R21, 2 and t minus tau. As the definition of convolution, x1 and x2 is x1 of tau and x2 of t minus tau d tau. x2 of tau and x1 of t minus tau d tau we can interchange because it is obeys the commutative property. Taking equation 1, R12, x12 of x2 of t minus tau dt, replacing the dummy variable t by the p. T as a p minus 2, x1 of p, x2 of p minus tau dt. Since it is an even signal, x of t is equal to x of minus t. So integral minus infinite infinite x of tau p, x1 of p, x2 of minus of tau minus p into dp. Minus of tau minus p. So s is equal to the integral minus infinite infinite x1 of p, x2 of tau minus p dp. Replace the dummy variable by the tau by the t. Tau by the t here, the x1 of p, x2 of t minus p into dp. Again, they replace the variable of the p and the tau. S is equal to x1 of tau and x2 of t minus tau dt. It's a correlation function. Correlation function. What we am saying here, it is a S. It is a S. Why I change the x1 of p and x2 of tau minus p is not the minus here. Tau minus p. When I am taking the minus off, we can take tau is a positive and the p is a negative value. Okay. Tau minus p. See this one. S is equal to. I'm changing the tau as a plus and the p is a minus. So one signal, another second signal changes to the folded function. Second signal changes to the folded function. The minus of tau minus p is both are the same. The minus of tau minus p. So minus, if I am taking it's a folded function minus p. That I assume is a S. Assume is a S. Tau is a plus and the p is a minus if I am taking. Okay. Whenever if I am taking the minus of the folded function. So both are the equal. When the R of tau, R12 of tau is equal to, the correlation function is x1 of t with the convolution of x2 of minus t. X2 of minus t. Then the extension of the autocorrelation function, autocorrelation properties is the last topic here. We have the autocorrelation function and the spectrum density is a Fourier transformation relation. That Fourier transformation relation is f1 of omega and f1 of minus omega. Why I wrote the f1 of minus omega? For correlation and the convolution, what is the relation here? R of tau is equal to, let I am taking the f1 of t convolution with the second signal is a minus of t. Apply the Fourier transformation here. What is the first one? F1 of omega, and second one is a product F2 of because it is a negative value is there, minus omega, or it is also equivalent of F1 of omega with F star of omega. So minus becomes is equal to F of omega squared magnitude. F of omega. Got it, my students? So the R1 of tau e power minus j omega t d tau, we can simplify this function is equal to this, or it is also equal to that pi into delta of omega, the Fourier transformation of the given signals. It is a 1 by 2. So 1 by 2 the function, the pi into delta omega. The another signal here, the Fourier transformation of a cross correlation function. F1 of omega, F2 of minus omega is F1 of omega and the F2 of minus omega, the Fourier transformation relation. Let us F1 of t is F1 of omega, F2 of t is a F2 of omega. Similarly, F1 of omega is F1 of minus omega, F2 of minus t is a F2 of minus omega. But according to the relation between of the convolution and the correlation, R12 of tau is F1 of t and F2 of minus t, my students. It's a very important equation, the relation between of correlation and the convolution. So F1 of t and star of F2 of minus t, the convolution in frequency, F1 of omega and F2 of minus omega. Therefore, R12 of omega is in terms of time domain function, F1 of t and F2 star, F2 of minus t. This is F1 of t, my dear students. It's a convolution of F2 of minus t. It's a Fourier transformation. You can write this. The Fourier transformation is F1 of omega and F2 of minus omega. Got it? And sixth one, graphically the R12 of tau is same as R21 of tau, where it is folded back about the vertical axis at t is equal tau is equal to 0. R12 of tau is equal to R21 of minus tau. We already seen is a folded function. Okay. When I was interchanging the 1 and 2 as a 2 and 1, you can change the sign of the tau here, minus the folded function. Okay. So the energy spectral density E is psi of f is equal to squared magnitude. Is a E is equal to integral minus infinite psi of f into df. And what are the effects of energy spectral density? This is joules per hertz, my dear students, units. What is the effects here? Let the energy spectral density of x of t be the psi x of f and y of t is the psi y of f. The signal x of t is applied at the input of the linear time invariant system. The y of t is obtained at the output. Let a linear time invariant system to be the ideal filter which has pass band from lower frequency to the higher frequency. That is, only signal will be passed without any effect of effect from the F2 of FL to the FH. Okay. So the integral minus infinite a change as even function, the 2 into sine 2 into the integral 0 to infinite psi y of f. In this function, see, if it is a symmetric for positive and the negative values, you can write as a minus infinite as a 2 into integral 0 to infinite minus 1. And this is a lower limit and it is the upper limit, you can assume, FL to the FH. The psi y of f is nothing but square root magnitude of y of f. And y of f is in terms of system transfer function, h of f and x of f, replace here, and psi of f. What is a system transfer function in this range? The value is a 1. So 1 into. So Ey of Ey is equal to 2 into integral FL to FH psi x of F into dF in terms of energy spectral density of input signal. Okay, when you can take the low pass filter. And the relation between the correlation and the convolution, again we got the same thing, but related to the noise, we can see the noise free in the correlation function. Convolution of f1 of t and f2 of minus t, f2 of minus t by r12 of t, we have r12 of t is equal to f1 of t convolution with f2 of minus t. As a definition of convolution, f1 of tau and f2 of t minus tau d tau. The dummy variables of tau in this above integral may be replaced with another variable x. Now I am taking with another variable x. f1 of x and f2 of x minus t and dx. Only I change that tau is x. Changing the variable t to the tau, we get f1 of t as a tau integral minus infinite to infinite f1 of x and f2 of x minus tau dx, x minus tau dx. Okay, and that is equal to phi 12 of tau. What is a phi there? It is a r12 n, r12 of tau. Here the phi 12 of tau minus f1 of t convolution with the f2 of minus t at the tau is equal to t is equal to tau, and similarly phi 21 of tau is equal to f1 of minus tau and star with convolution with the f2 of tau, f2 of t, t is equal to tau, that is a r21 of tau. So interchanging of minus here and the plus, and the phi 11 as autocorrelation function, f1 of t convolute with the f1 of minus t, t is equal to tau is equal to the correlation function of r11 of tau. It is somewhat difficult, my dear students, this equation. Forget about this one. Okay, there is a little bit confusion. Finally, what they are saying is r12 of tau, r12 of t is becomes of phi 12 of the tau, the t variable and the tau variable. Since f1 of t, f2 of t minus tau is a correlation function, we take this as a convolution function and it becomes of correlation function. Okay, correlation function saying that is a f1 of t and f2 of t minus tau dt. The x is nothing but the t here and the tau. The correlation, what is the correlation here? The r12 of tau only. That is, I am taking as a dummy variable of phi here, phi 12 of tau. Phi 12 of tau. See the correlation, convolution becomes to the correlation here. Okay, convolution becomes, it is a correlation function. Any one of the signal is a folded function. Either is a one or the second signal, first signal or the second signal. But both are not equal. So both are not equal when we can consider as in the convolution. Not the convolution, is a correlation. Correlation is only the equal 1 2 of tau is equal to 2 1 of minus tau only. It not obeys a commutative property. Remember, my students. And the detection of a periodic signal in the presence of noise by the correlation. Now we can consider that the periodic signals are affected by noise that finds finds in the fields of the application in the detection of radar and sonar signals. That the fields noise at the fields, the application in the detection of radar and the sonar signals. Periodic component in the sine waves and cyclical components in the ocean wave analysis. Okay, if x of t is a periodic signal and if x of t is a periodic signal and n of t represents the noise signal, then x of t is a periodic signal and n of t represents a noise signal. The periodic signals are affected by the noise that fields the application in the detection of radar and the sonar signals. And I'm assuming the x of t, s of t is a periodic signal and n of t is a noise signal. Is a power signal. It can represent limit t tends to infinite 1 by to the integral minus t by to the t by t. One signal is a periodic signal s of t. Another signal is a noise signal with a delayed version n of t minus tau dt for all the values of tau. At cross correlation function Sn of tau is equal to 0 means it is orthogonal to each other. Orthogonal to each other. So when the signal is 0, there is no any similarities between the two signals. The similarity is there in the between the two signals. We can call it as a cross correlation. So detection by the autocorrelation function. The same signal, if I am taking here, autocorrelation function, it is a shifted version. Let s of t the periodic signal and mixed with the noise signal n of t, then it is received signal is f of t is x of t plus n of t. The received signal f of t is a s of t plus n of t signal. The periodic signal is mixed with the noise signal. Let us say this is a periodic signal and the noise is added here. Noise is added. It follows that f of t contains a periodic signal of frequency displayed by the pi ff of tau. If pi ff of tau does exhibit such a periodic nature, it is possible to separate pi ss of tau and the pi nn of tau is a non-periodic component. So pi ss, ff is output signal, my students. SS is the input signal and it is added with the noise signal. SNN. FF is output, pi FF of tau and pi SS and NN. NN is a noise signal and SS is a periodic signal and FF is the output signal. Denoted the autocorrelation function of f of t, s of t and n of t respectively. Pi FF of tau is autocorrelation function for the output function. Limit t tends to infinite 1 by t the integral minus t by to the t by 2 with the signal f of t and f of t minus tau dt as the definition of autocorrelation function. What is the f of t? Is a combination of the two signals, periodic signal and the noise signal, s of t plus n of t, and second signal is also the combination of the two signals, s of t minus tau plus n into t minus tau dt. Replace the t by the t minus tau. And now they expand this function, the integral minus t by the t by 2, s of t with the s of t minus tau as an autocorrelation function of ss, and s of t and n of t is autocorrelation function of Sn and of tau, and n of t and s of t is autocorrelation function of n into s, and n into n is a autocorrelation function of n into n. So see all the four terms we got. S with the two functions, ss and Sn, n with the two functions, ns and the nn. Since s of t and n of t are uncorrelated functions, Sn and nn is not the autocorrelation functions, these are different signals, it is a 0 as we're saying here itself, n and s is a 0 value. S of t is a periodic signal and n of t represents the noise signal. Then the combination of these two signals, the periodic and the noise signal, is a 0. Replace that as Sn and Ns is both are the zero values. The output function, the autocorrelation of ff of tau is equal to ss of tau plus nn of tau. Exhibits a periodic nature at larger values of tau. It follows that f of t contains a periodic signal of frequency displayed by the pi ff of tau. If pi ff of tau does exhibit such a periodic nature, it is possible to separate pi ss of tau and the pi nn of tau. So non-periodic component. Okay, nn of tau is a non-periodic. Ss of is a periodic function. Follow my dear students. This is separating of the two functions. And this is a noise. Dotted lines I showed here is a noise signal. And SS is a periodic signal here below. And finally, after these two combination, we got the FF. You can separate this noise signal. You'll get the periodic signal. The last topic here, extraction of signal from noise by filtering. Extraction of signal from the noise by the filter. So a signal is masked by a noise can be detected either by correlation techniques or filtering. A signal is masked by noise can be detected either by correlation techniques or filtering. Correlation technique in time domain and the filtering in the frequency domain. See the cross correlator, take the two signals f1 of t and f2 of t to get it is a pi 1 2 of tau. Why I wrote it is a pi, it is R only, my dear students. Okay, don't confuse here. One time I am saying it's R and one time is saying it's a pi and another time it is a difference. 1 2 of tau, definitely that is a correlation function only. See here the 1 and 2 is there, that is a cross correlation. 1 1 is there, it is autocorrelation. And by using the filtering techniques, you can use a frequency domain. So what is a frequency domain? F1 of t is F1 of omega. And another, the internal we have taken that F2 of minus omega, and these two correlation function, convolution function becomes of a correlation function. Second signal is a minus. First signal is a plus value, is a folded function, is equal to the autocorrelation, cross correlation function. Okay, F1 of omega and F2 of minus omega is a frequency domain. Cross correlation in time domain and the frequency domain. The impulse response h of t of a system with the transfer function of F2 of minus. So h of t is equal to F inverse of F2 of minus omega. Actually, you have to get here the linear time invariant system h of t. Here the x of t. X of t with h of t, you'll get the convolution function in frequency is a product. So, but f2 of t is a Fourier transformation of f2 of omega, and f2 of minus t is a Fourier transformation of f2 of minus omega. What is the impulse function here? H of t is a f2 of minus t. The received signal f of t is with the combination of x of t, s of t, and n of t. Okay. Received signal of a time domain signal, it is f of t is equal to as a periodic signal x of t, and is added with the noise signal. We are filtering out all the noise signals and extracting the desired periodic signal x of t by a filter which allows only the frequency components present in is s of t to passes through. Okay, only it allows the frequency components present in the s of t, and it passes through the low pass filter or any other filter, we can say. Understood, my student? So c of t, you can take it is a waveform like this. So c of minus t is a folded function. Now the c of minus omega, it allows only the one frequency, that is omega as a positive value, and here the minus omega n, c of minus omega. You can take this example is passes through any signal. You can remove that noise signal, extraction of signal from the noise by filtering. The C of t you can assume here, and C of minus t as a folded function with a range of 0 to t, means it allows only that period, 0 to t period only. The remaining all it is a 0 it becomes, because we are passing this signal through the filter. It can passes only the low frequency values. It avoids the high frequency values. And in terms of the frequency domain, the positive value here and the negative values. Got it, my dear students? Now you can see there's some examples here. Some examples in the energy spectral densities. So determine the autocorrelation function and the energy spectral density. Determine autocorrelation function R of tau and energy spectral density for the given signal x of t is equal to e power minus at mu of t. Okay. For the given x of t, find autocorrelation function and energy spectral density. So what was the autocorrelation function formula? R of tau is equal to integral minus infinite to infinite x of t x star of t minus tau dt. Okay, this is a definition for the autocorrelation function. And if it is a real, it is a complex function I take. If it is a real, minus infinite to infinite x of t x of t minus tau dt. Okay. What is x of t given? Integral minus infinite to infinite e power minus at mu of t, as x of t can substitute. X of t minus tau e power minus a, the t now it is a t minus tau, and mu of t minus tau as second signal and the dt. What is the range of t values when you can replace the mu of t and the mu of t minus tau? We already know, my dear students, so mu of tau is equal to 1 for t is greater than or equal to 0. Mu of t minus tau is equal to 1 for t minus tau is greater than or equal to 0, and t is greater than or equal to tau, and tau is less than or equal to t. And t is greater than or equal to, and tau is less than or equal to t, means it is vary in between of the 0 to t. Okay, my dear students. Tau to less than or equal to and greater than or equal to. T is greater than. So t is less than or equal to 0 and less than or equal to tau. Okay. The tau is greater than, not it is a tau to the infinite, my dear students. See, I am taking the t is greater than or equal to 0 here, and tau is less than, or the t is greater than or equal to t. No need of again take this tau instead of this. So using these two relations, you can write the combined relation, the t is greater than or equal to 0 and t is greater than or equal to tau. Means greater than or equal to tau, and here it is that t is greater than or equal to tau. It becomes of tau to infinite. Tau to infinite, because is equal to 0 and it is a tau. So when these two are equal, not it starts from the 0 itself. From it is a tau. Actually, it starts from the 0 here and the tau is here. And combining, you can take from 0 to t and the tau to t. The overlapping occurs from tau to infinite only. There is no any overlapping of 0 to tau. So now the range is integral tau to infinite. Got it, my dear students? So if I am taking the mu of t is equal to 1 from 0 to infinite, but the mu of t minus tau with respect to the dt only here, the t is greater than or equal to tau. So tau to infinite. So overlapping occurs for these two combinations is tau to infinite. So e power minus at and e power minus at and e power plus a tau dt is equal to e power a tau is a constant and e power minus 2at. So e power minus 2at by minus 2a, and with the limitations of infinite and the tau, that is equal to e power a tau by the minus 2a. When I am substituting the upper limit, e power infinite is a 0. Lower limit, if I am substituting minus e power minus 2a tau, e power minus 2a tau. Got it, minus friends? With the minus and minus, it becomes of plus e power a tau and e power minus a tau. You get the e power minus a tau, e power minus a tau by 2a. Therefore, r of tau, the autocorrelation function r of tau for the given signal e power minus a t mu of t, got as e power minus a tau by 2a. Got it, my dear students? Now another one, the first one we find out the autocorrelation function, and the second one you have to find out the energy spectral density. Energy spectral density. What is the relation between of energy spectral density and autocorrelation function is Fourier transformation relation, psi of f. So psi of f is equal to Fourier transformation means minus infinite to infinite r of tau e power minus j omega. Omega is now it's a frequency here, the 2 pi f into t df, not the df, dt. What is r of tau? We got r of tau is equal to is a Fourier transformation relation. Because it is r of tau, don't put it is a t here, my dear students. It is also the tau only with respect to the tau, d tau, and here is a d tau. What is r of tau? We got minus infinite infinite e power minus a tau by 2a, e power minus a tau by 2a into e power minus j 2 pi f into tau d tau. So now the bases are same, exponential values is both are the tau. So 1 by 2a into e power minus a tau integral minus infinite infinite e power minus j 2 pi f tau into d tau. So now you can see it is a formula for the Fourier transformation of e power minus a tau. Is a Fourier transformation of e power minus a tau. What is a Fourier transformation of e power minus a tau? 1 by a plus j omega. Okay, a plus j omega. But here it is not given in the mu of t. When you can take it is a mu of t, definitely you can say that is a e power minus at mu of t. The Fourier transformation is integral minus infinite infinite e power minus at into e power minus j 2 pi f into t dt. Okay, but here the tau, here the tau is there and it's also tau. But there is no any multiplication factor of mu of tau, mu of t. So consider it as both the relations from minus infinite to infinite we have. Both we getting means 1 by, for the first value it is a plus, and for the second value you'll get the a minus. Okay, so e power minus a tau, you can take is a tau values is a positive values. Tau is value is a positive value. The integral becomes of 1 by 2a into integral minus infinity to 0. Plus tau value, if I'm taking the minus, becomes of a tau into e power minus j omega. Omega means 2 pi f into tau d tau. And second integral is 0 to infinite. So positive values e power minus a tau, e power minus j omega is equal to 2 pi f in tau d tau. Now the Fourier transformation of a tau and Fourier transformation of e power minus a tau. What it is, Fourier transformation of a tau minus 0 to minus infinite to 0 one value, and 0 to infinite is another value. What it matters, students. So now I'm taking here these two functions, e power a tau, take it is a tau as a common, a minus j, I'm taking it as a omega matters, students. So every time it is 2 pi f if I write a minus j omega, tau if I am taking common. Apply the integral for this, you'll get a minus j omega with upper limit is 0, lower limit is minus infinite. Substituting the upper limit is 0, 1 by a minus j omega for the first one. For the second function, you can observe here e power, what is a common factor there? Tau minus tau. Minus tau, we can take the common, a plus j omega. Apply the integral for this one, you'll get a plus j omega with upper limit is infinite, now the lower limit is 0. Upper limit you can substitute infinite, it becomes 0 minus, so minus 1 by a plus j omega we got. This is the second function. Now you can apply here. So r of, not the r of tau, r of tau is equal to, not the r of tau, is the energy spectral density psi of f is equal to 1 by 2a. For the first integral, we got 1 by a minus j omega, and second integral 1 by a plus j omega minus is equal to 1 by 2a. Take the LCM here, a plus j omega minus a, minus into minus is plus j omega, a minus a plus j omega, okay. And it is becomes of a minus j omega and a plus j omega. So a square plus omega square. So a plus b into a minus b means a square minus b square. If that minus becomes is a plus with the j square. Okay, j square value. A minus j omega is the first integral, plus for the second integral we can see e power minus, apply the infinite is a 0 minus 1 by a plus j omega, 1 by a minus j omega minus 1 by a plus j omega, a plus j omega minus a, and it is minus a get cancelled, 2 j omega by a square plus omega square and into 2a, the 2 get cancelled. The energy spectral density is j omega by a square plus omega square. Got it, my dear students? This is one example to find energy spectral density and the autocorrelation function. Okay. So very important example is there, my dear students. That is the second, the final expression. It is if x of t, the signal given a1 cos omega 1 into t plus theta 1 plus a2 cos omega 2t plus theta 1, then find out that r of tau is equal to a square by 2 cos omega 1 tau plus a square by 2 cos omega 2 tau, and S of F is equal to nothing but power spectral density. Power spectral density pi by 2 into a square multiplied with the delta of omega plus omega naught plus delta of omega minus omega 1, not the 1, not here, 1 is, plus its total function, my dear students, a2 square, it is a a1 square, it is also a1 square and a2 square. Again, it is multiplied with the delta of omega plus omega 2 plus delta of omega minus omega 2. Got it? First one is you can find out the autocorrelation function. Second one is the power spectral density. And the third one you have to prove P is equal to, that is the power spectral density, P is equal to x square of t whole bar is equal to a1 square by 2 plus a2 square by 2. So the three is a very important example. So definitely, if you hope you are lucky fellows, you'll get in the external examination also. See, this the first one is already did in the yesterday's class, my dear students. I take the x of t is a a1 cos omega 1 t plus theta 1 r of tau. You can get it is a a1 square cos omega 1 tau by 2. Similar way, the second one is a a2 cos omega t plus theta 1, that is a a2 square by 2 cos omega 2 tau. Okay, I already explained this one. So second one you can take, it's getting. So the first one we already discussed in the last class. Using this, you can find out the power spectral density and the power P is equal to. Power P is equal to. So what is the relation between of R of tau and power spectral density is a Fourier transformation relation, S of F. Got it, my dear students? S of F, Fourier transformation relation. So S of F is equal to, the Fourier transformation formula is there saying that integral minus infinite to infinite R of tau e power minus j omega tau df, d tau, my dear students, because it's a t only, the d tau. So omega is nothing but the 2 pi f here, 2 pi f. So now I'm taking the R of tau as a functions e power minus infinite to infinite. What we got, a1 square by 2 cos omega 1 tau, cos omega 1 tau plus a2 square by 2 cos omega 2 tau whole multiply with e power minus j omega tau d tau. Got it, my students? So the first, if I am taking the First one, a1 square by 2. What is the cos 1 omega 1 tau in the exponential value? E power j omega 1 tau plus e power minus j omega 1 tau by 2, and it is multiplied with e power minus j omega tau d tau. Is the integral of minus infinity to infinity for the first integral. What is the second integral saying that a2 square by 2 integral minus infinite to infinite. Second, it is e power j omega 2 tau plus e power minus j omega 2 tau by 2 whole multiplied with e power minus j omega tau d tau. Got it, my dear students? Two integrals we got. Two integrals. The first integral, see the e power j omega 1 tau and e power minus j 1. Both are is a basis or same. We can add the powers. Is equal to a1 square by 2 and whole multiplied with e power j omega 1 tau and e power minus j omega tau. What it matters, friends? So you can take as a minus e power minus j is a common omega minus omega 1 omega minus omega 1 tau plus second one is also both are is a minus only. Take the minus e power minus j omega plus omega 1 tau into d tau. Is the integral of minus infinite to infinite. Plus similarly minus infinite to infinite a2 square by 2 e power minus j omega minus omega 2 tau plus e power minus j omega plus omega 2 tau whole multiplied with the d tau. Now observe here, it is a integral Fourier transformation of 1 with omega is there. 1 with the Fourier transformation we know 2 pi into delta of omega. Okay. Now here the 1 is there with omega is omega minus omega 1. So that is equal to a1 square by 2. What is the first one? Fourier transformation 2 pi delta omega is omega minus omega 1 plus similarly for second also 2 pi into delta of omega plus omega 1 plus a2 square by 2. For here itself, it is also 1 with Fourier transformation 2 pi into delta of omega minus omega 2 plus 2 pi into delta of omega plus omega 2. Okay, either 2 get cancelled, you can take the common, and here also the 2 get cancelled, take the common. Now what is the power spectral density? S of F is equal to, final answer is A1 square pi into delta of omega minus omega 1 plus pi into delta of omega plus omega 1 plus A2 square pi into delta of omega minus omega 1 plus pi into delta of omega plus omega 2. What it might be, students? This is the second one. They're asking that power spectral density can show that pi by 2 a1 square delta. You got the same thing. Pi by 2 here itself. Pi by 2 is a1 square delta of omega minus omega 2 a2 square the pi. We take the common as a pi, my students here. Take the common pi by 2, a1 square is a pi and a2 square is a pi also. Got it. And this third one you can see Third one is the P is equal to A1 square by 2 and P is equal to. When we'll get the P, what is the relation here? The P is equal to R of tau at tau is equal to 0. It becomes of the power signal. What is R of tau? We got A1 square by 2 cos omega 1 tau plus A2 square by 2 cos omega 2 tau is equal to P at tau is equal to 0. You can keep the tau is equal to 0. What is the A1 square by 2 cos? What is the cos omega 1 tau? Cos 0. Cos 0 is a 1 plus A2 square by 2 and cos tau is equal to 0. On the 0 is a 1. Tau is equal to 0 is a 1. P. So P is equal to A1 square by 2 plus A2 square by 2. This is the third one. What it might students? A1 square by 2 and A2 square by 2 function. Following. Like that we'll get the function with 1. Already we have it is 2 and 2 to get cancelled is a pi into something. Okay. Any doubts is there? This is the completion of the 4th unit, my dear students. You can try the different examples if any there. Then you'll get the answers. Any doubts? Thank you.